Hello class, welcome to lecture 8. In this lecture we'll be discussing rotation. I have to say that most of the physics that we'll discuss in this lecture is not new. It is physics that we've discussed in previous lectures. It's just now applied to a different type of motion, rotation, rather than translation. So we've been dealing with translation so far, and today we'll look at another type of motion, rotation. So we know that with translation, an object can move in 3 dimensions. It can move in this direction, it can move in that direction, and it can move up and down. So there's 3 degrees of freedom regarding the motion, that is translation. With rotation, there's the same number of degrees of freedom of motion. There's 3. Those same 3 axes in which an object can move along in translation. An object can rotate about those axes. So an object can rotate about the axis that's running this way, so an object can rotate this way. The object can rotate about this axis, so it can rotate this way. And finally, an object can rotate about this axis, so it can rotate that way. So there's 3 degrees of freedom when it comes to rotation too. And just like in translation, where an object can be moving in all 3 directions at the same time, an object can be rotating about all 3 axes at the same time. Right? And so in realistic motion, whenever an object's moving, it could be moving translating in multiple dimensions, multiple directions, while also rotating about multiple axes, right? But we're only going to focus on motion rotating about one axis at a time. We're not going to look at multiple rotations simultaneously. So first we're going to talk about how we measure actual motion itself, or displacement. So we know with translation, displacement was delta x. That was displacement. Right? And our standard unit was meters. Well, in rotation, we're going to measure our displacement in terms of angle. Through what angle did the object rotate? So let's just say we have a simple disk, and it's going to rotate about this axis. So this is the axis it's going to rotate. And we'll say it rotates this way. And if we pay attention to a point on the disk, and this disk has a radius of r, let's say it rotates through an angle of theta. Now theta is going to represent the angle through which it rotates. Now this point on the edge of the disk, it moves through space along this arc. And we're going to call the length of that arc S. So S is the arc length traced out by the edge of that disk as it rotates through this angle theta. So now there's a relationship, a mathematical relationship between this arc length S, theta, the angle that traces out that arc length, and r, the radius of this arc. And that relationship is S equals r theta if theta is measured in units of radians. Maybe you've heard of radians before, maybe you haven't, but radians is the standard unit measurement for angle that we use in physics. And so you might ask yourself, well, I know that a circle has 360 degrees, right? So degrees is a unit of angle, and there's 360 degrees in 1 full revolution. There's 90 degrees in a quarter revolution, 180 degrees in a half revolution, 270 and 3/4, and 360 degrees in 1 full revolution. And so we know that 1 revolution is equivalent to 360 degrees. But what is a radian? How much angle is 1 radian? Well, if we think if this relationship is true, whenever angle theta is measured in units of radians. So if we solve this for theta, theta equals S over R. 1 radian is the angle at which S over R is equal to 1. So one radian of angle is the angle that traces out an arc length, S, that's equal to the radius of the circle. Now, arc length is a distance, radius is a distance. So if this is measured in centimeters, meters, inches, it doesn't matter, the units cancel out. So this ratio of arc length to radius is unitless. It's 1. So the radian is technically not a physical unit. It's what we call a ghost unit. It doesn't represent an actual physical unit. It's just a proportion or amount of a rotation. But it's the amount of one rotation that results in the arc length traced out by through a radius r that makes them equivalent. So that's 1 radian. Well, how much angle in degrees is 1 radian? Well, it turns out that 1 radian is just a little bit bigger. It's approximately equal to 57 degrees. It's actually just a little bit bigger than 57 degrees. All right, so 45 degrees is probably like right here. So maybe this is about 1 radian, what I drew there. Right? But that's clunky, right? Well, 1 radian is a little bit larger than 57 degrees. Is there a cleaner way to represent this? Well, yeah, let's figure out how many radians are in 1 revolution, okay? So if theta is the number of radians and equals S over R, 1 revolution, S is equal to the circumference of the circle, 2 pi r. And so if we plug in this into this equation for S, we get theta equals, for 1 revolution, is equal to 2 pi r divided by r. So we see that for 1 full revolution, where S is equal to 2 pi r, the circumference of the circle, that corresponds to an angle of 2 pi radians. So 1 revolution is 2 pi radians, or 360 degrees is equal to 2 pi radians. All right. So if 1 revolution is 2 pi radians, then half a revolution, 180 degrees, is pi radians. 90 degrees is pi over 2 radians. 270 degrees is 3 pi over 2 radians, and this is 0 or 2 pi radians. So we have 0, pi over 2, pi, 3 pi over 2, 2 pi radians. Now, you're asking yourself, all right, well, pi, what is this pi? Maybe you've heard of pi before, maybe you haven't. Well, just a quick explanation of this concept of pi. Pi is a very, people discovered pi a long time ago. It's an irrational number, which means it is a number with an infinite number of decimal places that represents the ratio of the circumference of every circle divided by its diameter. So the circumference is the distance around the circle, and the diameter is the length across the circle. So any circle in the universe, if you measure its circumference and you measure its diameter, and you find the ratio between them, you will get the same number, and that's pi. Right? And so, so we see this is how we get the definition of circumference, right? Because circumference equals pi times the diameter. Well, what is the diameter? Well, it's 2 times the radius. So the circumference of a circle is 2 times r times pi, but we usually write it as 2 pi r. So that's where the formula for the circumference of a circle comes from. That's just the definition of pi. Now, pi, what is that ratio? Pi is equal to 3.14159, and it goes on forever and ever and ever and ever and ever and ever and never stops, right? But this is the ratio of the circumference to the diameter of every circle in the universe. It's just one of those objective truths of the universe that make the universe such a beautiful place, that there are these like hard programmed numbers into it. So that's where pi comes from, right? And so 1 revolution is equal to 2 pi radians, right? So and 1/2 revolution, or 180 degrees, is equal to pi radians, and so forth. So that's how we measure angular displacement. It's in radians. So we measure angular displacement as far as rotation in radians. So for example, if we were to look at the rotation of my body about this axis, the axis that runs through the length of my body, if I would rotate this much, that's a 90-degree rotation, or pi over 2 radians. If I would rotate instead this much, that is 180 degrees, half a revolution, or pi radians. And finally, if I would rotate 1 full revolution, my angular displacement is 1 revolution, 360 degrees, or 2 pi radians. Now, if I keep on rotating, I would just keep on adding my angular displacement. Last example, if I start here and I rotate here, this is 2 pi. And if I stop here, my angular displacement would be 2 pi for the first revolution, plus another pi radians for the half. So my total angular displacement would be 3 pi radians. It doesn't stop at 2 pi and reset. No, it keeps on accumulating as you rotate, right? If you make more than 1 rotation, your angular displacement is going to be more than 2 pi. If you make 2 full rotations, your angular displacement would be 4 pi, for example. Okay, so delta theta is what we call angular displacement, and it's measured in units of radians. Okay, now we know what a radian is too. All right, so if an object is rotating, right, it is undergoing an angular displacement. Now it's undergoing that angular displacement throughout some time interval. And so, just like with translation, we can characterize the rate of displacement using a velocity in translation. We can represent the rate of angular displacement with not a normal velocity, translational velocity, but with a rotational or angular velocity. So just like change in position or displacement over time gives us a translational velocity measured in meters per second, we have a change in angular position or angular displacement over time. That is what we call angular velocity. And it's measured in units of radians per second. Okay? So what is this variable? So this is not a W. Looks like a W, it's like a curly W. This is the Greek letter, it's the lowercase omega. Okay? Capital, that's capital omega. Okay, of course, that's lowercase omega. So lowercase omega is the variable we use to represent angular velocity. And you'll notice I put the vector symbol above it because it's a vector just like velocity, so it has a direction. And we'll talk about that direction in a little bit. So if an object is rotating with the angular velocity of, say, 2 pi radians per second, what does that mean? Well, it means it undergoes an angular displacement of 2 pi radians every second. And so it takes 1 second to make one full revolution. If it has an angular velocity of, say, pi radians per second, then that means it's rotating pi radians every second. So if it starts here, rotating about this axis, it's going to rotate pi radians, which is 180 degrees, every second. So it will take 2 seconds to go 2 pi radians, right? Or it could rotate this way, whatever axis it's rotating about, right? So this is the rate of rotation, all right? So this is the angular rotational velocity, sometimes referred to as angular velocity. I put a slash there because both of these terms are used to describe this rotational rate of displacement. Okay. Now, just like with translation, our speed or velocity can change with time too, right? An object can speed up, it can slow down, its velocity can change, and we characterize or we measure the rate of change in velocity as an acceleration, right? A translational acceleration measured in units of meters per second squared. We can do the same thing with rotation, where a change in angular velocity is measured in what we call angular acceleration or rotational acceleration. And it's measured in units of radians per second squared. So if an object is rotating at a constant rate, it has an angular acceleration of 0, right? Because it's not speeding up or slowing down. However, if an object is at rest and then it starts to rotate, right, it must have an angular acceleration because its angular velocity is changing. So if an object is rotating faster or starting to rotate slower, if its rate of rotation is changing, it is experiencing an angular acceleration. And this is the Greek letter alpha, lowercase alpha. Capital alpha is an A, but we use the lowercase Greek letter alpha to represent rotational or angular acceleration. So these concepts are all the same, just applied to rotation. So if I make a table, so this is translation, and this is the analogous notation in rotation. For displacement, we have delta x measured in meters. For displacement rotation, we have delta theta measured in radians. For velocity, this is a vector, we have v measured in meters per second. For angular velocity, we have omega measured in radians per second. And for acceleration, translational acceleration, a measured in meters per second squared. In rotation, we have angular acceleration measured in units of radians per second squared. Okay. Now those relationships between these variables are the same too. So if you remember, acceleration is equal to v final minus v initial divided by t. So we can rewrite this as v final equals v initial plus a t. Well, that equation it translates directly to rotation, but instead of final translational velocity, it's final angular velocity equals initial angular velocity plus alpha t. Same equation, just using rotational variables instead of translational. And that equation for average velocity and displacement. So delta x is equal to average velocity times time. Displacement equals 1/2 v initial plus v final times time. We can write that in terms of rotation. The same equation, just written in terms of our rotational variables. So like I said, same physics, just applied to a new type of motion, right? Now, like I said, angular velocity and angular acceleration are vector quantities, just like translational velocity and translational acceleration are vectors too. So mathematically, positive or negative sign tells us what direction the velocity and acceleration are in, right? So if we, in translation, if we define an axis, right, we say, oh, this is the positive x direction, that's the negative x direction. Then if we say our velocity is 5 meters per second, that positive sign is telling us, oh, that velocity is in this direction. Or if our velocity is negative 5 meters per second, tells okay, our velocity is in the negative x direction. So with translation, the sign tells us, is it that way or is it that way? Is it this way or is it that way? Which way is it moving along an axis, right? But with rotation, we have to define our coordinate system, which way is positive, which way is negative, but the sign tells us which direction rotation is. Is the rotation this direction? Or is the rotation this direction, right? So we have to assign which is positive and which is negative, okay? Now, it's generally the convention, so if this is a rotation axis, so if something is rotating about this line, it goes into and out of the board, if it rotates clockwise, that's generally considered to be a negative. We generally consider clockwise rotations about an axis as negative. So I'll just, and then counterclockwise rotations as positive. You can define your coordinate system any way you want. You can reverse it as long as you keep your signs consistent. But the general convention is that a clockwise rotation, that's considered to be the negative direction, and a counterclockwise rotation is the positive. Now, how do we draw the vectors? Like we could draw a velocity vector. Say if this is the positive x direction, and velocity is 5 meters per second positive, then we could draw the velocity vector pointing in the positive direction. Well, how do we draw, or which direction do rotational vectors point? Angular displacement, angular velocity, and angular acceleration. Well, I'm going to draw it three-dimensionally. Let's say you have a disk that's rotating about this rotational axis. So it's rotating about this axis, this disk. So it's rotating. We're looking at it kind of three-dimensional. So the rotational vectors always point along the rotational axis. That tells us what axis they're rotating about. Okay, so if this is rotating this way, omega is going to point either this way or that way along the rotational axis. Angular displacement is this way or that way, and if it has an angular acceleration, it's either this way or that way. But which way is it? Well, to determine which direction the vector points, we use what's called the right-hand rule. And how the right-hand rule works is you take your right hand, that's the name, right-hand rule, and you pretend to grab the rotational axis with your 4 fingers and wrap them around the rotational axis with your 4 fingers. But this is important. Your fingers wrap around it in the direction that the object is rotating. So since the object is rotating around it this way, my finger is going to wrap around it that way. Okay? And whatever direction your thumb points on your right hand is the direction that the vector should be. So the angular displacement is in this direction, so is the angular velocity, because it's rotating in that way. Now, if an object was rotating in the opposite sense, right? Now, my fingers wrap around it that way, my thumb points down this way. So, its angular displacement is that way, so is its angular velocity. So here I'll ask you a question. If I rotate this way, what direction is my angular velocity? Is it pointing up out of my head, or is it pointing down through my feet? Well, okay, we'll take your right hand and I'm rotating this way, so wrap your fingers around my rotational axis in the direction I'm rotating, and your thumb points up. So my angular velocity and angular displacement vector is pointing this way. I was rotating the other way. You've got to wrap your fingers around this way in the direction I'm rotating, and my thumb points down. So now my angular displacement and angular velocity vector are pointing down that way along the rotational axis. All right, and then angular acceleration points along the axis corresponding to the right-hand rule in the direction it's speeding up or slowing down. So if an object was rotating like this, but its angular acceleration was that way, then that means that because angular acceleration and angular velocity are pointing in opposite directions, this object is rotating this way, but it's slowing down. It'll come to a stop, and if it keeps on accelerating in that direction, it'll begin to rotate in that direction, where its angular velocity will now have flipped, and these two vectors will point down that way. Or at least its angular velocity will. Okay. So just like with translation, if the angular acceleration and the angular velocity point in the same direction, then it's speeding up. If they're pointing in opposite directions, it's slowing down. So if I start here at rest and I start to rotate this way, then my angular velocity is this way, so is my angular acceleration. Right? If I'm already rotating this way, my angular acceleration is up. But if I start to slow down, that means my angular acceleration is down, right? My angular acceleration must be in the opposite direction as my angular velocity in order for me to be slowing down. I come to a rest, and if I keep on accelerating, having an angular acceleration down that way, I'll begin to speed up and develop an angular velocity in this direction. All right. Let the fluid in my inner ears settle down and busy. All right, so that is the direction that our angular velocity and acceleration vectors point. They follow the right-hand rule. Okay, so we talked about angular velocity, angular acceleration. Now we're going to move on to torque. Okay. So we know that if an object is going to move per Newton's second law, the object's velocity is going to change. It's going to have an acceleration per Newton's second law. There must be a net force, right? And that net force is proportional to the object's acceleration, and the object's acceleration is inversely proportional to the object's mass. So we understand that. And the same concept is true with rotation. Okay? If we want an object to rotate, right, something has to, if we want the rotation of an object to change, we need something to cause that change in its rotation. Because just like Newton's first law applied to translation, an object at rest stays at rest, an object moving in a straight line at a constant speed will stay moving in a straight line at constant speed. That applies to rotation too. An object at rest is not going to spontaneously start to rotate, right? It's going to stay at rest. And if an object is rotating about an axis, it's going to want to continue rotating about that axis at a constant speed. because the object has mass, it has inertia. So Newton's first law of motion applies to rotation, just like it does for translation. As does Newton's second law, right? That if we are going to change the rotation, if it's going to start rotating if it's at rest, or if it's going to speed up or slow down if it is already rotating, that means something has to cause that change. So we need a torque. Oh, I can't use the proportional sign because that's the same as a torque causes alpha. So torque is analogous to force, but in rotation. Now, what is torque? Let's say if we have a disc and we want to rotate, and let's say the disc can rotate about this axis of rotation right here. If we want to rotate that about this axis, we're not going to push or apply a force in this direction along the axis. Even if we apply a force here and pull this way, that's not going to cause it to rotate. If we apply a force here, that's not going to cause it to rotate. If we apply a force here, that's not going to cause it to rotate. That's not going to cause it to rotate. If we apply a force here, none of these forces are going to cause it to rotate. What we have to do in order to cause it to rotate is we have to apply a force that's a non-zero distance from the rotational axis. We're going to call that distance r, wherever that distance is, and that force has to have some amount of it that's perpendicular to the line that connects the rotational axis to the point the force is applied. So if we'll apply a force F in this direction, that's still not going to cause it to rotate, right? If this is allowed, if this is a wheel that's allowed to rotate about this axis, if I apply a force there, you can see how it doesn't rotate. However, if I rotate that direction that applied force, now, if I apply a force, if this is free to rotate about this axis, I apply a force at a distance r from this rotational axis down, that wheel is going to start to rotate. That wheel is going to experience, a wheel or disc is going to experience a angular acceleration. So torque is produced by applying some force at some distance from the rotational axis, and that force has to have a component to it that's perpendicular to that line that connects the rotational axis to the force. And so torque, we use the Greek letter tau, capital, this is the capital Greek letter tau to represent torque. And it's equal to the product of the force applied by the lever arm. R is the lever arm. That's the distance between the axis of rotation and the point at which the force is applied. Okay? And this equation holds true if the force is perpendicular to the lever arm. If the force isn't perpendicular to the lever arm, then this isn't true. You have to use some trigonometry, but that's beyond the scope of this class. So we're always going to treat the force as being perpendicular to the lever arm. And the torque provided by that force is applied at that distance is equal to the simple product of the force and the lever arm. Now, so you can increase or decrease the torque by increasing or decreasing either the force applied or the lever arm, right? So if you have a given force, you can increase the torque resulting by the force by increasing the lever arm. So if we apply that force not here, let's say if we apply the force at double the distance, 2r, now we have, in a sense, doubled the torque because we doubled the length of the lever arm. In colloquial terms, we increased our leverage, right? If you further out, you get more power, more torque as you increase your leverage. That's why if you go to open the door, right, if here's the hinge of the door, it's much easier to open and shut the door if you push on the edge of the door furthest from the hinge, because you apply a force perpendicular to the lever arm. So here's the rotational axis. The door is rotating about this axis. If I apply the force close to the axis, my lever arm is very small. So I can apply a really large force to generate an angular acceleration. However, if I apply the force out here, I can apply a much smaller force and generate the same angular acceleration. Why? Because I have a much longer lever arm. So that's why it's easier to open and shut the door by pushing at the far edge of the door, pushing or pulling at the far edge of the door, as far from the hinge, the rotational axis, as possible. So what are the units of torque? Well, force is newtons, and lever arm is the distance in meters. So it's units of Newton meters. Hey, Newton meters sounds familiar. Wasn't that work? Like a force applied to a distance? That's Newton meters, but through a displacement? Yes. And we called a Newton times a meter, we called that a joule. But in terms of torque, we keep it as Newton meters, because the big difference is this force isn't being applied to this displacement. It's not moving along that displacement. That's the lever arm from the distance from the rotational axis that the force is being applied. And remember, for work to be done, the force had to be parallel to that displacement. So the object had to be moving through that displacement, and the force had to be parallel. But with torque, the force is perpendicular to that lever arm. So it's a completely different principle. The units are the same, newtons times meters, but we keep it as Newton meters for torque, and we write it as joules for work. In English units, the units of torque are foot-pounds, right? So foot and then unit of mass, pounds. Pounds is unit of force, foot unit of length, foot-pounds. So how many foot-pounds of torque? So that's what causes an angular rotation, potential angular acceleration. So if you had some object that's about to rotate about this point, so this is the rotational axis, we apply, and this has a distance of 1 meter, that a force of 3 newtons is applied, and the torque is equal to F times R, which is equal to 3 newtons times 1 meter, 3 Newton meters. Okay? Now, torque is a vector too. And what is the direction of that vector? Well, we use that same convention. Is this torque going to cause a clockwise or counterclockwise rotation? Well, this torque, as I have it drawn here by this force, it's going to cause this disc to rotate that way. So that rotation is a clockwise rotation, so this torque would be negative. If this is the axis rotation, this torque is causing it to rotate counterclockwise, so that would be a negative torque as well. And if we were to draw it, it would point into the board along that rotational axis, following the right-hand rule. If we would reverse the direction of this force, say if it was 3 newtons this way, now that torque is going to try to rotate the object, or whatever it is, this rod, this direction, which is counterclockwise. So that would be a positive torque, and it would point this way out of the board instead of in the board, following the right-hand rule. All right. So we can rewrite Newton's second law in terms of torque and angular acceleration. So torque, okay? So it's very similar to Newton's second law. This is the net torque, because there could be multiple torques. So this is very similar to Newton's second law in translation. But we have this inertial value here, this inertial parameter. That's the mass of the object. The mass of the object tells us how much acceleration results from a given net force. Or in other words, how much net force is required to accelerate a given amount of an object with a certain inertia. Well, we have that same rotational term for, inertial term for rotation. We call it the rotational inertia. And this is the inertia associated with rotation. It's not simply the mass of the object, right? Because you can imagine an object that has a mass that has different amounts of inertia, rotational inertia, about different rotational axes. So, for example, imagine a barbell. And it has the big plates on it. Now, is it easier to rotate that barbell about that axis? So you're trying to rotate that barbell about this axis? Or is it easier to rotate it about this axis? Rotate it this way. It's much easier to rotate the barbell about the axis that runs along the length of the barbell than it is about an axis that runs through the middle of the barbell, rotating this way. Why? Because the rotational inertia is basically a function of how far the mass is from the rotational axis. So if we're rotating about this line, we have these two 45-pound plates that are far from the rotational axis. So it takes a lot to get them to start moving. They have to move a lot through space in order to rotate. However, to rotate about this axis, the mass is more closely packed around the rotational axis, so we don't have to get as much mass moving through space to get it to rotate. So the more closely compacted the mass is around the rotational axis, the smaller the rotational inertia. The more spread out the mass is about the rotational axis, the larger the rotational inertia. So if the rotational inertia about my body is smallest about this axis, because if you look, my mass is much more closer to the rotational axis that runs through the length of my body. So all my mass is pretty close to that rotational axis. However, I have a much larger rotational inertia, say about this rotational axis, right? I have mass that's really far from that rotational axis. So it takes more torque to rotate my body about this axis than it does this axis. Same way about this axis. I have pretty much the same rotational inertia about this axis as I do that axis, right? It would take about the same amount of torque to rotate me this way as it would this way. Say this pen, it's the smallest rotational inertia is about this axis, where the mass is much more closely compacted around this rotational axis, where it has a larger rotational inertia about this axis and this axis. And now the rotational inertia is even larger about, say, this axis. If we wanted to rotate the whole thing about this, it has even more rotational inertia. So the axis doesn't always have to run through the center, geometric center of an object if we're going to rotate it. So we could rotate an object about any axis. And so this would have an even larger rotational inertia. Right, so that's the inertial term, the rotational inertia, and it's dependent on the object, the shape of the object, and where the rotational axis of the object is. So we seem to have a conceptual understanding of that. But that's Newton's second law applied to rotational motion, right? Where translation, net force is equal to mass times the resulting acceleration. So that's in translation. In rotation, the net torque is equal to the rotational inertia times the resulting angular acceleration. So by net torque, you're going to have an object, right, that has one force F1 and one force F2. Now let's say if F1 and F2 are the same magnitude, then which one provides what's the net torque going to be? Well, the net torque would be, well, F1, this wants to rotate it clockwise, so the torque due to F1 plus the torque due to F2 The torque due to F1 would be negative F1R, right? Let's just call this F1. Well, F2, but F1 equals F, let's say the magnitude is the same. Plus the torque due to F2 would be F1 times R over 2, and that's positive because F2 is trying to rotate it about this axis counterclockwise. So the net torque is going to be negative F1 R over 2. So the net torque is going to be in this direction. So the torque due to F2 takes away some of the torque due to F1 because they're opposite directions. You can see how they're trying to rotate this disc about this axis in opposite directions. This is trying to rotate it that way, or this torque is trying to rotate it this way. But because this force is double the distance from the rotational axis, it generates a larger negative torque than this force is generating a positive torque because it's only acting half the distance from the rotational axis. So this would have a net torque that's negative, and so the resulting angular acceleration would also be negative. Okay? Because the angular acceleration is always going to have the same direction as the net torque. So just like how you have to add up all the forces and see what the net force is to find out what the resulting acceleration is, you have to add up all the torques to find out the net torque. And so this allows us to draw an expanded free body diagram. Or let's say you have a plank and it's supported by a cable, and there's a person standing on that plank. Okay? Now it's at rest, it's not moving. We always, if an object is uniform density, we assume its weight, we can represent its weight as acting at its geometric center, or its center of gravity. So this is the mass of the plank times gravity. Okay? I'm going to draw a coordinate system. Let's say this is positive x, this is positive y. Now, and now this person, they have a weight. It's acting on this plank. Oh, I'm going to call this a board. Mass of the board. And this is the mass of the person times gravity. And in these cables, there's going to be tension. Tension 1 and tension 2. Now, if this object isn't moving, that means its acceleration is equal to 0. And its angular acceleration is equal to 0. Therefore, the net force must equal 0 newtons. And the net torque, it's a weird looking tau, net torque must also equal 0. Right, so this is our expanded free body diagram, where it's called expanded because usually when you draw a free body diagram, you draw all the forces acting on the center of gravity of the object. Right, there would be normal force, and this is some force, all acting from a point. Where here, we're drawing the forces where they're acting in space. Now because it's not moving, it has no linear or translational acceleration, no rotational or angular acceleration, we have these two things, and we say that the object is in equilibrium. Equilibrium, if its acceleration is equal to 0, and its angular acceleration is equal to 0. And these are the two conditions for equilibrium. The net force must equal 0, and the net torque must equal 0. And remember, you can apply Newton's second law in both the x and the y direction. So the net force in the y direction equals mass times acceleration in the y direction. The net force in the x direction equals mass times acceleration in the x direction. And since the acceleration overall is 0, both the net force in the x and the net force in the y must equal 0. So the net force in the x direction, well, there's no forces acting in the x direction, so that makes sense. In the y direction, the net force in the y direction, that equals Well, T1's positive plus T2. And then these forces are acting down, so it's minus the mass of the person times gravity, the weight of the person minus the weight of the board times gravity. So this must equal 0. So let me draw this down here. So T1 plus T2 minus MBG minus MPG must equal 0. So that's one equation we have. Now, we also have that the net torque must be equal 0. Now, it's not rotating about any axis. So the net torque about any potential rotational axis must be 0. So net torque about this axis is 0. Net torque about this axis is 0. This axis, any axis is 0. Now we know torque is force times that lever arm. So we could look at the net torque about any point. But if we choose a rotational axis in which an unknown force goes through, then that force applies no torque, and it's eliminated from the equation, which is strategic. Okay, so let's call this point A. And let's say that this board has a length L, and this is the center, so that's L over 2, and this is L over 4, the distance to the person. So this net torque about point A. So what forces generate a torque about point A? Well, T1 is acting at point A. So this tension generates no torque. So we can forget about it. We're going to have the torque due to MPG plus the torque due to MBG, the weight of the board, plus the torque due to T2. And this is all the torques about this point. And so what are those torques? So the torque due to the weight of the person is equal to the force times the lever arm. So that's mass of the person times G, its weight. The lever arm is this distance, L over 4. And is it positive or negative? Well, this is trying to rotate clockwise about point A. So that would be a negative. Now, the torque due to the weight of the board is the weight of the board times the lever arm. That distance is halfway across the board, so that's L over 2. And that's also trying to rotate it clockwise, so that's a negative torque. And finally, T2, it's acting in the distance L, and that's trying to rotate it counterclockwise, so that's a positive torque, and that must equal 0. And now you can see L factors out of every term, and you could divide it out so that length, we don't even care how long it is, we just care about the proportional distances these forces are acting. If I move this over here, you get negative MPG minus MBG, oh, this is over 4, this is over 2, plus T2 equals 0. So assuming I knew the mass of the person and the mass of the board, I could solve for the T2. I can find out what this tension is. T2 equals G times MP over 4 plus MB over 2. Right? And that's that's acceleration times mass, that gives me a force. So that's what this tension is. And because I have the tension, T2, from applying the sum of all torque about, I could have found the sum of all torque about this point and found T1. If I try to find the sum of all torque about this point, I have two unknown forces, T1 and T2, providing torques, and I'll have two unknowns in the equation, which will be hard to solve. But now that I have T2, I could plug it into this equation to find T1. And if I do that, go over here, I found from the sum of all torque about A, that T2 is equal to G times MP over 4 plus MB over 2. And Newton's second law applied to the y direction is T1 plus T2 minus MPG minus MBG equals 0. I can plug this in for T2, T1, plus, I'm going to just distribute that so it's easier, G MP over 4 plus G MB over 2 minus MPG minus MBG equals 0. So T2 equals, well, this is MPG negative, this is positive MPG over 4. This gives me a negative 3 MPG over 4. I'm going to take it over that side. I get a positive 3 MPG over 4. And here I have a negative MBG and a positive MBG over 2. So this gives me a negative MBG over 2. Take it over to the side. Get a positive. So, oh, this should be T1. So T1 equals G times MP over 4 plus MB over 2. Checking here, make sure I did my math correctly. Oh, I forgot it. I was like, I knew I made a mistake because T1 was equaling T2. I was like, well, that can't be the case. This is a 3. I forgot that 3. So here, if I write T2, if I write it down below so we can compare. This makes some intuitive sense. Oh, man. Let me write it here. Okay? This makes intuitive sense because T1 is supporting kind of 3/4 of the weight of the person and half of the weight of the board, where T2 is supporting 1/4 of the weight of the person and half of the weight of the board. Why that makes intuitive sense is because the weight of the board is acting halfway in between T1 and T2, so that load is shared equally between the two. That's why this term is the same. However, the person is closer to T1, so T1 has to support more of the weight of the person than T2 does. And because of where the person is located, the person is located, and so that T2 only supports 1/4 of the person's weight, while T1 is supporting 3/4 of the person's weight because the person is located closer to T1. If that person stood in the center, then this would be MP over 2, MP over 2, because they'd be equally supported, that person's weight would be equally supported by T1 and T2. So as the person walks this way or that way, these fractions change, 3/4, 1/4, corresponding to where the person is relative to T1 and T2. So if the person was over here, L over, if this was L over 8, so 1/8, right? T1 this would be 7/8, and this would be 1/8, right? Or if it was a third, if they were a third, this would be 2/3. This would be 1/3. So those tensions support the amount of weight of the person depending on how close that person is to each cable. So this is how we could solve problems using expanded free body diagrams. So engineers have to use this physics all the time to make sure that objects aren't going to rotate in part of structure, like the different members of structures and so forth as they construct them. But to make sure not only is it not going to move due to Newton's second law applied for translational motion, but also Newton's second law applied for rotational motion. Because if something's not supposed to move, we don't want it to move up and down, left or right. We also don't want it to rotate. Alright, so that brings us to rotational kinetic energy. So if an object is rotating, it's moving. So it has energy. Just like if an object is translating, it has energy associated with motion. And so kinetic energy for translational motion is 1/2 mv squared. Well, for rotational motion, it's analogous. We just translate this into rotational quantities. So it's 1/2. The inertia term for rotation is inertial rotation. So remember, rotational inertia, I is the rotational inertia. And remember, that's dependent on the rotational axis and the shape of the object. And instead of v, it's omega squared. So the more rotational inertia and the larger the angular velocity, the more rotational kinetic energy the object has. Okay, so for example, if a wheel is rolling down a hill, not only does it have a velocity, but it has an angular velocity too. And as it rolls faster, it not only does it have a translational kinetic energy, but while it's rotating down the hill, it's going to have a rotational kinetic energy. Oh. Wherever the rotational inertia of the wheel is times its angular velocity squared. So objects that are rotating have kinetic energy associated with the rotation too. So this is easy enough to calculate if we have the rotational inertia and the angular velocity. So that's the rotational kinetic energy. So it makes sense for moving, we're going to have it has energy. And then we have angular momentum, which, well, let me just make a comparison here. So kinetic energy for linear motion is 1/2 mv squared, that's for translation. For rotation, it's 1/2 I omega squared. And just for rotation, kinetic energy is a scalar. It doesn't have a sign, positive or negative. So rotational kinetic energy doesn't have a sign either for rotation. For momentum, we have linear momentum is equal to mass times linear or translational velocity. We use capital letter L to represent angular momentum. And as you might guess, it's I times omega, the inertial term times the angular velocity. Now, if an object has, say an object of mass m is moving along a circular path of radius r at a velocity v. So its momentum, linear momentum is mass times velocity. And to get its rotational or angular momentum, we just multiply its linear momentum by r. And r times m, remember I said the rotational This is the angular momentum of an object, a singular object, rotating about a point. Alright, so this is just a singular object rotating about a point. So like a satellite in space or a planet orbiting a star. This is how you find the angular momentum. In what direction is the angular momentum? Well, it points along the rotational axis. If it's moving that way, you use the right-hand rule. L points this way. If it was moving that way, L would point that way, following the right-hand rule. This term for angular momentum applies to a body that's rotating about an axis. So not an object rotating along a circle, but let's say if we had a disk rotating about an axis, it would be the moment of, so it would be the rotational inertia of that disk multiplied by the angular velocity, the rate at which it's rotating. That would give us the angular momentum of that rigid object. Right, so you couldn't use this for my body. What is the angular momentum of my body? Well, because I'm not a single mass rotating about a point, right? Rotating about this. My whole body is rotating about this axis rotation. However, if I was on a merry-go-round and my body's moving around, rotating around that point, you could calculate the angular momentum of my body using this, where this is my mass, this is the speed I'm traveling through space, and this is the distance between me and where the merry-go-round is rotating. However, for the merry-go-round itself, you'd have to use this equation, because the whole object is rotating about that axis of rotation and with the angular velocity of omega. And so the total angular momentum of the system would be the angular momentum of the merry-go-round plus the angular momentum of my body. That would be the total angular momentum of the system. Angular momentum of the rotating merry-go-round and the angular momentum of my body moving around the circle. Okay. Now, just like linear momentum, angular momentum is conserved as well, unless there's a net torque, external torque. And so this is a really interesting phenomenon, and we use it all the time. For example, we spin a top, and so a top starts rotating about this axis of rotation. While it's rotating, the top stays upright. If the top isn't rotating, if it's not rotating, what happens? It just falls down. Why does the top stay upright if it's rotating, and it falls down if it's not rotating? Well, that's because when it's rotating, if it's rotating here, I wrap my fingers around the axis of rotation, the direction it's rotating, it has an angular momentum, L, that points that way. Now, angular momentum is conserved unless there's a net external torque. There's no torque acting on this top, so angular momentum is conserved, so it stays rotating upward. The angular momentum is not going to change unless there is a net torque, and that's what allows the top to stay upright, is the conservation of angular momentum. Same concept on a bicycle, right? On a bicycle, the wheels rotate this way as you move forward. So they have an angular momentum that points, in this case, into the board in that direction. And because that angular momentum wants to be conserved, if the wheel were to topple over, then the direction of L would have to change. And that's a change in angular momentum. And so the wheel actually resists turning over, falling over, because that would require net torque. There's no net torque. And that's what allows you to balance on a bicycle as you're riding a bicycle, is the conservation of angular momentum that helps keep you upright. Where if you just sit on a bicycle and if you're not moving and put your feet up, what happens? You fall over, right? It's that conservation of angular momentum that helps you stay upright, helps you balance. Right? That's the same thing with the Earth. The Earth's rotational axis is tilted. So here's the sun. The Earth, its rotational axis is tilted. So say if it rotates this way, L points that direction. As it rotates around the Earth, so here's the equator. So here, the southern hemisphere is getting more sun, so it's summer down here and winter up here. 6 months later, the Earth is over here. Its rotational axis doesn't change, right? It's still pointing in the same direction. There's the equator. Here, the northern hemisphere is getting more sunlight than the southern hemisphere. It's summer here, winter down there. So the rotational axis of the Earth doesn't change. It stays. If the Earth is rotating this way, and the tilt of Earth's rotational axis is 23.5 degrees off of the plane of perpendicular to the plane of the solar system. And so Earth's rotational axis, I'll use this, is tilted, and it stays pointing in the same direction as it rotates around the sun. And it's that tilt and rotational axis that gives us the seasons. And that's why it always points towards Polaris, the North Star, right? If the Earth's rotational axis went like this, then the southern half of the Earth would always be facing the sun, and they'd have perpetual summer, we'd have perpetual winter. Or if it rotated like this, then the northern half of the Earth would always be pointing towards the sun, and we'd have perpetual summer, and the southern hemisphere would have perpetual winter. And the stars in the night sky would always be changing, right? It not only would be changing with the season, well, they'd be changing, but like North Star would no longer be the North Star. It'd be north sometimes, and it'd be pointing off in some direction. North Polaris would be over here in the night sky instead of directly ahead 6 months later. So the conservation of angular momentum keeps objects that are rotating wanting to keep that rotational axis to stay fixed. And that allows gyroscopes to work too, because you have a rotating disc, and as the housing moves, the rotating disc, because the conservation of angular momentum, its rotational axis stays the same, so you can see how you are rotating around that rotating disc, and it allows us to orient ourselves in space. That's how a gyroscope is used to orient say an airplane or a submarine, where you can't see your surroundings. Say, well, am I rotating? Am I oriented this way, this way, this way, this way? The gyroscope allows you, because it always has this fixed direction, because of the conservation of angular momentum. And another application of the conservation of angular momentum is because angular momentum is the product of the moment or the rotational inertia and the angular velocity. If we change the rotational inertia, the angular velocity has to change accordingly so that the angular momentum is conserved if there's no net torque. So an application of this is if you've ever seen a figure skater, right, and they're twirling, right? They're twirling on the ice. They're rotating about this rotational axis. Now, if they hold their arms and their legs out, that means their mass is more widely distributed about the rotational axis, so they have a larger rotational inertia, which means they have a smaller angular velocity. Right? But as they pull their arms and their leg in, what they're doing is their mass is less distributed about the rotational axis, so it's more compact, and so it reduces the rotational inertia. In order for angular momentum to be conserved, the rotational or angular velocity must increase. So that's why they begin to spin faster. So there's no net torque acting on them. Nothing, there's no torque that's causing them to speed up, to have an angular acceleration. That's not caused by a torque, that's caused by a conservation of angular momentum. If they put their arms back out, they slow down, pull them in, they speed up, put them out, slow down. Now, if you're ever at a playground and you're on a merry-go-round, or if you're on one of those things where you sit on it and you spin, you can play with this by putting your legs out. You'll spin slower, you'll rotate slower, put your legs in, you'll rotate faster. Slow, fast, slow, fast. You do it even on a rotating chair on the conservation of angular momentum. So if you change your rotational inertia, your angular velocity has to change accordingly so that angular momentum will remain conserved. Okay, so that concludes lecture 8 on rotation. Thank you very much. Well, let me just write this down here for completeness. I forgot linear momentum and angular momentum. Okay, now that really concludes our lecture.